Okay, so previously in our first session, so you have looked at what is data structures, right, and algorithm, okay, an overview, and then we also look at what is the pointer, right, and after pointer, then we also look at what is a general linked list, because in the first workshop we are looking at linear data structures, right, which include linked list, stack, and queue. So in the first session, we have looked at linked list, general linked list, okay, where you can insert and remove item from anywhere or any position, okay, in the list. And after that, we also look at stack, okay, which is a specialized list where you can only insert and remove the item from the beginning of the list only, okay. Beside that, we also look at the implementation, right? How can you implement a list or use a list, okay, by using the STL, the standard template library provided in C++. Okay, so we have looked at linked list and also stack, and now we will continue with queue. Okay, so queue is another specialized list, right, where the insert and remove of the item can be done at a certain position, either beginning or the end. Okay, so that's why it's special. Usually, if you go to the internet and find for queue, right, the insert operation is called an queue, and the remove item or the delete operation is called the queue. Okay, so what is a queue? A queue is, okay, if when you insert an item, right, you can only insert the new item at the end of the list, okay, as the last node, right? You can see from here. And when you remove an item from the list, you can only remove the first node from the list, or this is the dequeue operation. Okay, so you have to follow this rule. You cannot insert and also remove, or the enqueue dequeue. You cannot do it in any other location beside the end and also the beginning. Okay, then because of this, queue has the property of first in, first out, FIFO, right? Okay, so for queue also by stack, it is less general than list, because you cannot perform any random insert and delete in other position except the end of the list and also the beginning of the list, right? And it will be easier to implement because of this, because you have less cases that you need to consider. Okay, now why do we want to use queue, right? Why do we want to use queue? Okay, or why do we want to study queue? Because there are also a lot of problems, right, that have this first in, first out characteristic. For example, queuing up when you are going to the bank, or when you queue up to buy food, or you want to pay in the supermarket, or even like in terms of computer, okay, the print queue, especially if you are using a network printer, right, where everyone is sharing the same printer, right? So this person can send, and then person two also can send their job or the document to be printed. So all these jobs will be put in a queue, okay, so that whoever send first, it will be print first. Okay, okay, you can also use it, let's say like the landing of the airplane in the airport. Okay, they also follow a queue. Okay, like who will land first, right? So you can also use queue to put to wait for their turn. Okay, so if you want to implement queue, right, using STL, okay, you can also look at the member functions that is provided. You can go to this link here. Most of the function members that you can use when you use queue. Okay, so let's look at some example. How do we implement the queue, right? Okay, just like stack or our linked list just now. First, you need to include queue, okay, at the top here of your program. And then after that, when you want to create a queue, right? Create a queue, the syntax, you put queue, then followed by the bracket, where inside the bracket, you have to specify what data type you want the queue to store. So here we create a queue that store integer, then this is the name of your queue. Okay. So just like the stack and the linked list, when you just created this queue, if you check whether it's empty or not, right, it will be empty because we haven't inserted any items inside yet. Okay. Then after that, okay, just like for stack also, there is no iterator provided in the STL for queue, because for queue, we are not supposed to traverse as well. I mean, when you use queue, right, usually you want traverse the queue, means go to every node. Okay, because you use queue, you want to like simulate the queue where you just have to insert at the end and then you remove the item from the beginning. Okay, so there's no iterator provided as well. Okay, then okay, let's look at how can I enqueue some item or insert some item to the queue. Okay, so I will use a for loop where I'm going to insert, let's say, integers from 1 to 5 to my queue. Okay, so inside the for loop here, what I'm going to do is, if I find that if my queue is empty, then I will just print out so that I know, okay, now my queue is empty. Then when I first insert the first item, what is inside and so on. So after that, the enqueue operation means to insert an item to the queue. In the STL libraries, right, is called push as well, just like the stack. But don't be confused. This push here doesn't mean that you will beginning, because what you are using now, the data structure here is queue. So push is to insert item, but if this is a queue, you have to this item will be inserted at the back of the queue or as the last node. Okay, just like the name is the same only, it's called push. Okay, so when you push means you enqueue the new item to the queue. Okay, and after that we try to see out. Okay, after I insert this value I to the queue, so we look at what is in the front of the queue and the back of the queue. Okay, for a stack just now, right, you can see that you have this function called top. When you call it, it will return to you the top item in your stack, right, which is actually the last item that you inserted to the stack. So for queue, because you see, when you insert, you have to insert at the back of the queue, and when you remove, you have to remove the first node, right, the beginning of the queue. So you have to keep track of both ends of the queue, right? So that's why here you have this front function and the back function. Okay, if you call the front function, it will return to you the first node in your queue. Okay, the beginning of the queue. And if you call the back function, it will return to you the last node in your queue. Okay, the back of your queue, right? Okay, so here I will try to print out what is the value in the front and the back of the queue every time I insert, I mean a value to the queue, and then also the size of my queue. Okay, so this is the output after I execute this for loop here. You can see that initially it will print the queue is empty and the size will be 0 because we haven't inserted any value inside. So after I call the queue.push I, where my I is 1 now for the first time, it will print this message after inserted value 1 to queue. The front of the queue will be 1 and the back also will be 1, because now you only have 1 node inside your queue. And the size of your queue is 1 because you only have 1 node, right? Then, okay, when I loop the second time, my I becomes 2. I push value 2 to the queue. So after that, it print out, okay, after I insert value 2 to the queue, the front of the queue is still 1. But the back of your queue becomes 2 now. Because then from here, you can see the new item that you push to the queue or insert to the queue, right, it will be put at the end of your queue. Because when you print the back of the queue, you get 2. Right? And then the size of your queue is 2. Okay, then you just continue. I becomes 3. Then you can see that the front remain the same, is still 1, right? But the back now becomes 3 because the new and the size become 3 as well. And when your I becomes 4, then the same thing happens. The front is still 1, but the back of your queue is 4. And when you insert the last value inside 5, okay, the front of your queue is 1, but the back of your queue is 5. Okay, and now you have 5 you can say 5 items inside your queue. Okay, so this is how you can insert items. Okay, you just have to remember the new item will always be inserted at the back of the queue, right? Okay, now I want to remove all the items in the queue just now after I inserted the 5 items, right? Now let's try to remove all the items from the queue. So I will use a while loop and check as long as my queue is not empty, right? I'm going to just remove one item becomes empty. Yeah? And then here I will, every time I remove an item, before I remove, I will print out what is in front first. Because remember, when we insert item to the queue, it will be inserted at the back, right? But when you want to remove, you have to remove the first one, the front. Okay, so that's why I will print what is in the front first. Is I'm trying to print out what I remove. Okay, that's why I put queue.front. And then to remove this first node from your queue or the front one, the function is called pop, just like the stack function, right? But of course, the pop here for queue is to remove the first item from your queue. Okay, so you call pop, so it will remove the front item from your queue. Then I will check every time after I pop, right? If the queue becomes empty, it becomes empty, then I will print the queues becomes empty. If not, I will print what is the front and the back of the queue after I remove one of the items. Right. So let's look at the output. So from here, we can see that after removing item 1 from queue, the front of the queue now is 2. Initially, the front is 1, right? We have 1, 2, 3, 4, 5, right? And the back of the queue is still 5. Okay. Then when my eye become, when I look again, okay, because my queue is still not empty, then I will see that after removing item 2 from the queue, the front of the queue now is 3. Just now you see previously, the front of the queue is 2, right? So when you remove the second time, this 2 will be removed. And now the front becomes 3 and the back is still 5. Okay, then you just continue because your queue not empty yet. So the next move will be item 3 because it's in the front, and then the front will become 4 after you remove 3. Okay, and the back of the queue is 5. So after that, you loop again, then you are going to remove 4, and then the front now becomes 5, and the back also 5, which means you only left 1 item in your queue when your front and the back is the same value, right? So after that, when you remove the last item from your queue, this 5, then it will print the queue now becomes empty, and this while loop will be terminated. Okay. Okay. So these are some of the basic that you can use from the STL libraries for queue implementation. Okay. You can, try yourself, okay, if you have time to create a queue, and then you just call the insert and remove operation, the push pop here also called push pop, okay, and just try it yourself so that you can better understand it. Okay. Okay, so so far we have looked at the 3 types of linear data structures, linked list, stack, and queue, right? Okay, and now because previously we just look at how do we actually if we want to use linked list, stack, queue, how do we create this linked list or the stack or the queue, okay, using the STL libraries. And then how do we use some of the basic operations that is provided inside the STL libraries, right? Okay, to see like how to insert items, how to delete items, how do I print the content of the list, okay, and so on, just some basic operation. Okay, so now we are going to look at how do we actually use these linear data structures, right, to solve certain problems. We will start with linked list. Okay, we will look at one example how to use linked list. The example here is actually to use linked list to represent this polynomial expression. Okay, so previously when I talk about list, right, one of the usage is mentioned that it can be used to represent polynomial expression, right? Okay, for example, if I want to represent this polynomial expression like x power 2 y power 3 plus 3x power 5 y power 2 minus 9x plus 6. Okay, so how do I represent this? I can use a linked list to represent it, where you can see here, this is how the linked list looks like, where inside every node, right, every node will be used to represent one of the expression here, right? Okay, then and because inside every expression here, you have the coefficient and the exponent x and y, right? Okay, so we will have three, you can say, sub items inside the items. Okay, let's look at more example. Okay, for example, how first I need to create a structure to represent the coefficient, the x and exponent y inside the polynomial expression. So I will create this struct polynomial where inside I have three members, the coefficient to represent the 8, like for example, to represent this 8x power 2 y3. Yeah? Okay, so this 8 here is the value for the coefficient. And then exponent x, the power, right, for the x, exponent x is 2. And for exponent y, the value, the power is 3, right? So I just put 3 here. Okay, so this is how we represent the expressions inside the polynomial, right? Okay, so that's why for this, okay, let's go back to the previous slide. Okay, so this is coefficient, this is exponent, exponent x and exponent y, right? So from here, you can see that this 600 is to represent which part? 6 here. Because for this 6 here, your x, y both are power 0. That's why we don't show the x, y. And then this minus 910 is to represent this part here, 9x, minus 9x. Okay, where the coefficient is minus 9, your x is power 1, but your y is power 0. That's why you don't have the y here. And then this 823 is to represent this one, 8x power 2, y power 3. And 352 is to represent this 3x power 5 and y power 2. Right. Okay. Now, so we have this structure created so that we can use it to represent the polynomial expression, right? Okay. Then after that, okay, what we want to do here in this program is actually we want to write a program to store polynomial expression, right? In a linked list, and then we try to write a function that can help us to add two polynomial expressions together. For example, if let's say the first polynomial expression you have is this, we call it as poly 1, let's say, and the second one is this poly 2. So after addition, we restore the result of the addition inside poly 1. So this is addition, right? You can only add, for example, this 3x power 3y2. So you look at in the poly 2, do you have any expression that is of the same power with exponent x and exponent y? Like x power 3y power 2. You have one, right? This 9x3y2. So this 3 and this 9 will be added together, the coefficient, it becomes 12, right, after addition. So here, this x power 3y power 2, the coefficient now after the addition is 12. So this is how we add the two polynomials together, right? Okay, so we have written a program called polynomial.cpp that allow us to do this. Okay, so first I will let you see how the whole program looks like. Then only we will go to each part and try to understand it, right? Okay, I will use my Visual Studio. Of course, you can use any editors that you want. Okay, so over here you can see, okay, this is my structure definition. Okay, you can see here I include my list here. Then my structure definition for the polynomial I put at the top. Then here I have some function, okay, that help me to do certain things. Okay, but let's look at the main function first. So in the main function, so what I do first is I will declare a list, two lists actually, to help me to represent the polynomial 1 and polynomial 2 expression. Then I will create these two array here that represent the value for the coefficient and the exponent x and y for each of the polynomial expression, okay, that I put using something like, right? Okay, and then after that, I will insert the polynomial expression in P1 that is stored in P1 to my poly1. Then I do the same for poly2. That is the expression, the value is stored in P2, right? And after that, I try to print out what is inside my poly1 list and my poly2 list. Okay, are they representing the polynomial expression that I want, right? So we print out first. After print out, then I will call a function that we write to add two polynomials together and pass in poly1 and poly2. And the result of the addition will be stored in poly1. Okay, so after addition, then I will print out what is inside poly1 because the result is stored in poly1, right? So we print out to see whether our addition is correct or not. Okay, then after that, I will use this function called sort, because if you can see from here, right, my polynomial expression is arranged according to the exponent x, like x power 3 first, then x power 2, x power 2, then x power 1, and this one will be x power 0, right? So I want to arrange in this way according to exponent x value. Some sort like I want my list to be sorted using this exponent x, you see? Okay, so that's why here, because after the addition, it won't be sorted according to exponent x. But in the STL list, there is a function called sort that you can call that help you to sort the linked list according to ascending order. But the thing is, because our linked lists are not storing just one integer inside the node, is what you call that, what I store inside every node, you can see, is a structure type, right? So that's why if you just call sort and pass in your poly1, it cannot work one because it doesn't know how to sort these three things, right? Unless what you store inside here is just one integer, yes, you can. You can just call poly1 the sort, then it will help you to sort. But it doesn't mean that if your linked list structure type or a user-defined data type or complex type, okay, you cannot sort. What you can do is you can write a function. I call this function, I call it as compare x. That will help you to compare, because I want to sort according to exponent x, right? So this compare x will sort according to the exponent x here. So when you call the sort function in the STL, inside that sort function, it will actually based on this compare x function that we write ourselves to sort our list according to exponent x. Okay, so this is how you can use the sort. You can play around with it when you have time. Then I print out poly1 again just to make sure that my lists are sorted according to exponent x. You see? Okay, so then I also have here to help me to print my polynomial expression, my output. And I also have this function add to poly that will help me the two polynomial expression in one. Okay, so let's look in the explanation for each of the part here. So okay, so what I need to do is, of course, include the list and then create the structure, right, to represent the polynomial expression. Okay, if you want to have more exponent, you can add, or you just want to try with one exponent, you can take away this exponent y. Okay, just with exponent x also can. Okay, then in the main, right, okay, create two lists that store polynomial type. Okay, where inside every node you will have coefficient exponent x and exponent y. So the first one is called poly1, the second one poly2. Then this array P1 and P2, right? This P1 5 means that the first polynomial expression that I have, right? You have only 5 expressions. It is actually this one, this first one. I mean my example is using this one, 3x2, 3x3y2, then plus 2x2y3, 1, 2, 3, 4, 5. Okay, so how do I represent this value, these 5 expressions in the array? It will be something like this. Like this 500 is to represent the 5. This one is minus 3x. This is 7x power 2, y power 2, and so on. Okay, so then this P2 is for the second polynomial expression that I'm going to store in poly 2. Okay, then and then this part here, I want the value for each of the expression in poly 1, the coefficient, exponent, x and y, right? So I'm going to use this push front, okay, means that every expression will be put every time, it will be stored at the beginning of this list here. Okay, so P1. For the poly 2 is I push P2, right? So I inside to poly 1 and poly 2. So after that, right, my poly 1, then I want to know what is inside poly 1, right? Because after insert, so we try to find out what is inside my poly 1 and also poly 2. Okay, so when I print out my poly 1, will contain polynomial expression. This is how we print out. Because when we print out here, we cannot have x power 3 in superscript, right? So I just use this symbol to represent the power. So inside my poly 1, I have 3x power 3, y power 2, plus 2x power 2, y power 3. Then, and so on, okay? Same also for poly 2. It will print out the polynomial expressions inside that I store inside poly 2, okay? So, after this, right, after we check, then we call this function add2poly. So this add2poly function, I will pass in the poly 1 and poly 2, the 2 expression. And then here, like just now what I told you, after that I will print out poly 1, right? Because the result of the addition will be stored in poly 1. Okay, so you can see after add poly 1 and poly 2, poly 1 now will contain the result of the expression, which is this one. And you can see the result, they are not sorted each of the expression according to the power of the exponent x, right? Like the first one, the exponent x, the value is 0. The second one, the exponent x, the power, the value is 2 and 4. It's not sorted, okay? So that's why I will call this sort function, okay, in the provided in the STL for list, and then I pass in my comparison function. It's like this comparison function is to tell this sort function how you want to sort your list. Because now inside your node in the list, you are not storing one integer or one float, means one data only. You are storing multiple data because it's a structure. You store coefficient, exponent x and exponent y, right? So that's why this compare x is to like indicate that, and it calls exponent x. Okay, then we print poly 1 again. So after the sort, when you print poly 1 again, at the bottom here, you can see that the x is sorted. I mean the expression how it arranged for x power 3 and 0. Okay, so this is this part. Okay, let's look at the print function, because just now you see when I call the print function, it will print my polynomial expression in this, in this format, right? So this print function we write ourselves. Okay, so how do we write it? So I need an iterator so that I can traverse to every node. Okay, every node in my list is storing one of this expression now, right? So I need to go to every node, take out the coefficient and the exponent x and exponent y value, and then see out in this manner, right? Or in this format here. Right, so that's why you can see here after I create the iterator, then I check if my list is not empty. If the list empty, means there's nothing inside, so we don't have to go through with the rest of the code because nothing you can do. We just return false. Else, if my list not empty, there's something inside, I'll go inside. Okay, I will iterate this list one, which is my, let's say I'm printing poly one, so it's my list one. So what I do, I will set the iterator to the beginning, the first node, and then until the last node, right? Okay. So every time, how I print, okay, why my inside the for loop, why I have to put C out here, and then after that I have checked the coefficient. If it's more than 0, I have to put a plus, then put a minus. This is because, okay, this part here, if let's say I'm printing the first node expression, then if this 3 coefficient is a positive value, I don't put +3, right? So that's why I have another C out just to print the coefficient. Okay, followed by X, then this sign, and then the exponent X value, the power, and then Y, the exponent Y value, the power of the exponent Y. Okay, then how about this one? Okay, if this is not the first node, then I will go else part here, but inside I still have 2 cases. If my coefficient is more than 0, I have to print a plus. Else I have to print a minus, right? So this one here, the first C out, is to print something like this. Because my 2 is positive value, so I have to put plus 2x power 2 y power 3. Then this minus 1, this one is to print something like, because this 3 here is a minus, right? Minus 3. So when I print the expression, I have to put minus 3 power 1 and so on, right? So that's why I have another C out for me to print this minus coefficient, okay, or negative coefficient. Okay, so this is my print. And for the function add 2 poly is to help me to add 2 polynomial together and store the result in the first poly, the poly 1. Okay, to do this, I need 2 iterator. This iterator 1, IT1 is to iterate this poly 1. Iterator 2, I make it to iterate poly 2. Okay, so how do I actually add 2 polynomial? Okay, you can see here my for loop, I will start with poly 2. Okay, I start with poly 2. So I go through every expression or every node in poly 2. Then I will, inside this, I have another for loop where I will go through poly 1, right? So for every expression in the poly 2, I will compare to the every expression in poly whether the exponent x and y match or not. Okay, this if statement you can see. If both the exponent x and y for this poly 1 and poly 2 are the same one, then I can add their coefficient together here. Okay, and then means that I found this same polynomial expression with exponent x and y the same in poly 1. So if I found, I will break. Means that the rest I don't need to check if I can find. Okay, but if I cannot find this, let's say in my poly 2, I have one expression 3xy2, but poly 1 doesn't exist. Okay, or let's say in poly 1, I have this expression 3xy2, but poly 2 doesn't exist. Then I have to insert this in poly 1 as well. Okay, so that's why you have this part here. Okay, so after that, then another function that we can look at is this compare x, like just now I explained to you, because we want to sort the polynomial expression according to exponent x, right? So that's why here we can use the sort provided in the STL, but because our is not a simple data or simple data type, so that's why you have to provide your own comparison function, where in this compare x function, you indicate inside the data in the main list, you want to compare against what? Like against exponent x. So it will help you to sort according to exponent x. For example, if inside your linked list, every node you store a student information like name, the age, okay, and let's say the IC number and so on of the student. So when you want to sort this student list, right, you need to select one of the attribute to sort. Like you want to sort according to their mean, or you want to sort according to their age, and so on. So then you write your own compare function, and inside the compare function, you indicate you want to sort according to what. Okay. So this is something like this. So here we sort according to the exponent x only, right? So this is the full output of this program polynomial.cpp. So if this is my poly1 and this is my poly2 expression, so after the addition, this is what I get from the programmer, but it's not sorted according to exponent x. I want it to be sorted, so I call the sort function, and after that you will see that my expression is sorted according to exponent x. Okay, but not y. Like for example, my exponent x power 2, I have 1, 2, 3, right? With the y exponent different power, but it's not sorted according to the y. You can write another function to do that, okay, if you want to be sorted. Okay, so this is how we can use a linked list to represent this polynomial expression. Okay, so that you can perform operation to the polynomial expression. Like here, we just look at addition only. You can, of course, if you need, okay, add other operation to it, like maybe subtract, okay, or maybe you want to evaluate. Let's say given the value for x, y, you want to know this expression will be evaluated to what value. You can also do that. Okay. Okay. Now let's look at another example. Using a stack. Okay, using stack. So for the stack, I'm going to use the example. How do we use the stack to check for proper pairing of bracket? Okay, so this proper pairing of bracket will be, okay, let's say for example, you is given an expression, a mathematical expression like this. Okay, when you write this expression, if you use bracket, the bracket is to indicate, okay, which part you should evaluate first, right? If you don't put bracket, then it will evaluate according to the precedence of the operator, like plus first or minus first or multiplication first, all these. Okay, so certain time we want, I want to evaluate this u minus b first. So you need to put a bracket. Then it will try to evaluate this first, right? Okay. So when you write this kind of expression, you need bracket must match. Let's say you have 3 opening, then you must also have 3 closing, right? You have opening, then you must have closing. And then not just that one, you also have to make sure that the type must be the same for this opening and for this closing. Okay, it cannot be your opening is curly braces, but your closing is a different one. It's a square bracket. Then it doesn't match, right? Okay, and also a proper formula can be this one, right? This one, the first expression, you can see that everything match. Okay, this is proper. Okay, not proper formula will be parenthesis. First is parenthesis doesn't match. Parenthesis here will be the bracket. Okay, here doesn't match will be, okay, like this one, u minus b, this part here, you can see that here you have a round one, but the closing one is a bracket one. It doesn't match. Like this one is a bracket, then the closing is the round one. It also doesn't match, right? Okay, then another way that it doesn't match will be everything match, but you have 1 extra opening. Means you have 4 opening, but you only have 3 closing. It also consider it's not properly, I mean, the parenthesis is, it is not, it doesn't match up, right? Okay, besides extra opening, you can also have extra closing, right? You can also have this kind of case with extra closing. So this one also consider not proper formula. Okay, so we will write a program that will help us to actually check the proper pairing. Okay, let's see how can we use that to help us to check for the proper pairing of the brackets. Okay, let's say the input to your program will be a string that contain this formula, the mathematical formula. So you will go through every character in this string, starting from the first one, okay? And when you go through, right, if the character is not opening or closing, you just ignore it. Like the first one you encounter will be this Y. So it's not closing or opening, so we just ignore, we do nothing. Okay, then equal also is not opening or closing, so you do nothing. Then the next one when you encounter is an opening bracket. So when you encounter opening bracket, you are going to push it to the stack here. Then you continue to read, okay, X and plus is not opening, closing, we ignore. Then the next one you read after that is another opening bracket. So you will push it to the stack. The next one also opening, you will push it to the stack, right? And then you will encounter this U minus B, so we will ignore this part. We do nothing. And now, okay, the next one that we read is a bracket also, but this is closing. If it's a closing bracket, you don't push to the stack. So what you do? Okay, if it's a closing, then you are going to pop one item out from the stack and compare with this closing here and check whether their type match or not. Okay, so when you pop, which one you will pop here from all the opening bracket that you have pushed inside, the top one, right? And the top one now is this round bracket. So you will pop this one out and then match with this closing, and they are the same type, so it match. When it match, okay, then it's like you go to the next step. Okay, if match, you do nothing, means so far what I found, everything match. Then the next one I read is this division and then 4. Okay, I'll ignore. Then the next one after that is another closing. So this part match already, okay. So after that, when I read this closing, the square one, every time you encounter a closing bracket, you are going to pop one item up from the stack. So the next one I pop will be this one, okay. And I will compare with this closing that I encountered here, and they're the same type, right? So means it match, and it means this part here actually, I mean, everything match, no problem. So the next one I read will be another closing, a curly braces. Then I'm going to pop one item out from here. And the type that I pop out with this type closing is the same. So means it match. Okay. What if, let's say I have one more closing here after the curly braces. If I have one more closing here, then I'm supposed every time we encounter a closing, I'm supposed to pop one item out from the stack, right? But when you try to pop, you see what happened? Your stack is empty, right? There's nothing that you can pop. So what does it mean? It means this is for the case where you have extra closing cases. Okay, when you encounter a closing braces, but when you try to pop something out from your stack so that you can compare, there's nothing for you to pop out. Then this one also, it's like you return false to indicate that your pairing of bracket is not proper. Okay. Okay, what if you have extra opening? How do you detect this case? Extra opening, it will be, okay, you will push everything inside. Let's say you have 4 opening, so you push 4 items inside, right? Okay, after you read the last closing, you pop one item out from the stack and then you match with the last closing. Okay, then does it mean because all those opening and closing that you pop out, everything match? But then after that, right, you still need to check one more thing. After you read everything in this expression, you will check, do you still have anything in your stack? If you still have, but you have reached the end of this expression already, you check every character already, then it means what? If you still have something in your stack, it means you have extra opening, because there is no closing that you can encounter to match with this opening here. You see? Okay, so when we write the program, we have to consider all these cases. Okay, what happened if you have extra opening? What happened if you have extra closing? Besides just checking whether the opening and the closing they match or not. Okay, so to to the program that we write to solve this problem is here in this parentheses.cpp. And this is the full program. Let me show you. This is the one. Okay, so basically this one, I don't have any other function that I need. Everything is just in the main. Okay, so this is the whole program only. So let's look at the program. What happened? Okay, we will start from the beginning. So of course, here, as usual, we need to include the stack because we are going to use stack. And then I will declare a string to when I ask user to enter the statement with parentheses, right? So I'm going to read the string and then store in this string here. Okay, and then I will create a stack, okay, called S. And what do I store in every node in my stack? I store a character. The parenthesis is actually a character, or the bracket is actually a character, right? And this variable result is actually to tell me when I check this value is a bool value, or it's either true, false. So when I check if it's true means everything match. Okay, if it's false means something doesn't match. Okay, then after I declare everything, then here after I read like the user enter, like for example this one here, if this is what user enter in a string, so I'm going to read every character from this string that I store in this variable line, which is a string, right? A C string. So I check character by character starting from Y, then equal, then this curly braces, and so on, so on. So every time when I check every character here, if I encounter an opening, what we have to do, you see, if line I equals to this round bracket opening, this square bracket opening, or this curly braces opening, I will push to the stack, line I, right? Just now I show you the step, right? So whenever you encounter opening, you push it to the stack. Then if you encounter closing, whether it's a round square one or a curly one, if it's a closing, so what you do, you need to pop something out from your stack, right? You need to pop something out from your stack. But then, remember I told you, okay, you have to check if your stack is empty or not before you access the top here, okay? Because if not empty, then means there's still some opening parentheses inside where you can pop out and compare. But if it's empty, means you don't need to. Okay, if you look at your if statement here, this is to test whether it match or not, right? The first condition you check is actually, is your stack empty or not? Okay, let me go to the next slide, because next slide will show you in more details. Okay, this one. So if your stack is empty, right? Then you don't have to execute this second part in your if statement. This is an or, right? If this is true, this part no need to evaluate, because if it's empty, there's no top anymore, right? There's no item in your stack, so there's no top, right? Okay, but if it's not empty, then only you will access the top and then like check whether the opening and the closing they match or not. Okay, so the thing is, if empty, then actually, if it's true, you go inside the if statement, you set the result to false to indicate that something doesn't match, right? But if it's not empty, you will pop out the opening and compare with your closing, right? So how do we compare? If you look at this, you see this second statement, if my one is not empty, I'm going to check the top element in my stack, which is one of the opening, right? And how do I compare? Actually, I should compare whether if what I pop out, if it's a round one, then I check this line I, the closing one that I read, is it also round one? If round one, then it match, right? But if it's not round one, it's a square one or curly braces one, then it doesn't match. But here I don't really have to check case by case. So what I do, I use this statement s dot top minus line I. So what this statement actually do? S dot top is what I pop out, the opening one. I minus with this line, the closing one that I read. So you see, because both of these are character, can we perform arithmetic operator on a character? Actually, you can. How? Character can be minus or can be plus? Yes, for character, yes. We will use the ASCII value to do that if you perform arithmetic operation. Okay, ASCII value is a value that is associated to each of the character or the symbol that you can use in the program, right? So here we have the opening and closing of the round bracket, this square bracket opening and closing, and closing. And if you look at the ASCII value, all these are opening and closing of the same type, right? If you minus the opening and closing, their value is less than 3. Like this, say for now, minus 28, 29, the difference is 1, right? Here we don't look at positive or negative. That's why we put ABS. Same also for the bracket here. Okay, this is 5A and 5E minus in hexadecimal. If you minus, the difference is 2 only. Same also for the curly braces. So it cannot be more than 3. So if it's more than 3, it means what? It means your opening and closing doesn't match. It can be your opening is this one. If your closing is the square, when you minus, definitely it will be more than 3. Okay, so this is how we check. Instead of checking the cases one by one, which can be very long. Your code doesn't mean cannot, but your code will be longer, okay, and not that efficient. Okay, so after we check something doesn't match, so you set your result false. But if it's false, means it matches, then you will go to the else part and pop. Means when it match, what you pop out will be taken out from the stack so that you can compare the next one. Okay. Then after this, after you check, then you're supposed to print the result at the end is either false or true. False here means something doesn't match in your expression, the bracket. True means everything match. So here, under what circumstances I print false? Okay, after I check this, right? Okay, if my result, if this is true, this one true or this one, if the result is false here, then means it's true, you will print false, right? Or even your result is true, but your stack is not empty. Remember just now, I told you, if your stack not empty, after you check everything, it means you have extra closing. So that's why we check the second condition here. So you also print false, okay? You have extra closing bracket, okay? So here why we have this while loop, because we want to pop everything out if your stack not empty, so that we can start from empty stack again. Okay. But if all these are false in if, then means everything the true result. Okay. So this is how we can use that to help us to check for parentheses, right? In this mathematical expression. But then you can also extend your program, the one that I showed you just now. Okay, you can use it to check even a source code. Like for example, our CPP source. After you write your step, what you do? You compile, right? When you compile, what is the purpose of compiling? Or because we want to check our syntax correct or not. So one part of the syntax that we check is the bracket that we use, right? For example, if you have let's say a function, you have open, do you have close or not, right? Or even like for loop, you open, you close or not, right? Or let's say you have if else statement or else if statement, all these is everything nested properly, okay, with the bracket and everything. It will also check for that one, right? So you can also use the program just now, but of course you need to change change something like the input. You open this file to read, you read character by character. When you encounter the opening, then you have to check for a program, right? What type of opening bracket do you have? Like We can also have this type, the round one, the curly braces one, the square one, and so on. So you add all the type, and then just like what we do just now, if it's opening, you put in a stack. If it's closing, then you pop out and check. Okay, so do this on the HTML source code as well for your web page. There's also a tag, right? Yeah. You have opening, you must also have closing, right? For the HTML source code. Okay, so you can always extend the program to do this as well, right? Okay, let's go to our last example using Q. How can you use Q to solve some problem? Okay, the example for Q, I'm going to use simulation. Okay, so first let's look at what kind of queue can we create. We can create a single queue. For example, you have customer form a long queue in a bank that have multiple bank tellers, which is a counter. Okay, this one is every counter has its own queue, the diagram here. But usually in bank, like you go inside, you take a ticket and then you wait, right? It's like we are waiting in a long, all of us are waiting in the same queue, right? And there are multiple counter. So you wait for a number to be called, right? So this is single queue only. Multiple queue, there are two types. Queue where all the queue are the same type. For example, like when you queue up to pay in a supermarket, right? You always, because there are so many queue, every counter has, so usually you will choose which one is the shortest, then I will join. Or you can have a multiple queue where every counter is of different type of queue of different types. Like the queues at the food court where every store is selling different food, right? And every store also has its own queue. Okay. So our simulation here, we are going to look at single queue. So single queue, let's look at the scenario that we have. So in this scenario of our simulation, we have customer queuing up in a bank. Okay. So in this scenario, we have 3 counters in the queue, in the bank, and then only 1 queue. So whenever you go to the bank, okay, you will join this queue because there's only 1 queue, and this bank only open 3 counters. Okay. So why we want to do this kind of simulation program? Because we want to find out, okay, let's say for a bank, right, it wants to know, let's say under this, it has peak hour and also non-peak hours, right? For example, if peak hours, okay, if I want to open 3 counters again, and of course, I will check, okay, I assume that every minute, how many customers will arrive at this peak hour, let's say, and then I only have 3 counters, and then I also will take into consideration, let's say the probability for every counter to serve the customer is like how fast every customer will do the transaction in every counter. We use a probability value to determine this. We can set this, but of course this value can be changed when you run the simulation. So then, okay, we run the simulation, then we want to know, okay, after, let's say I run for 100 minutes, let's say we look 100 times to represent 100 minutes, and we want to know at the end, right, how long is the queue? After that, if based on this scenario here, if the queue is too long, then it means maybe 3 counters, it might not be enough. Maybe I need to increase more counter, for example. Okay, so you can do this kind of simulation to find out. So in our scenario here, or our example here, we have 3 counters and 1 queue. Then at the start of every minute, when we run the simulation, we count how many minutes we run. So in every minute, we assume 3 customers will arrive to the bank and join the queue. And then for every counter that we have, we use probability of 0.3. Okay, the counter can finish serving the current customer. And here it says that the banker want to visualize the queue content, right? Like what I say, why we want to do this simulation. Okay, let's see how actually the detailed step of how we do this simulation. Okay, at the start of every minute, there are only 2 steps involved in every minute, and we are going to repeat step 1 and step 2 in every minute again and again. So in our scenario, I have 3 counters 0, 1, and 2, and I only have 1 queue here. So the first step is what? First step is DQ all customer from the counter. Okay, you might have some customer in the counter. Of course, first minute you don't have anything, but later you might have some customer that means counters 0, 1, and 2 are serving some customer. So how do we DQ? And how do we determine, okay, should I DQ customer from counter 1 or counter 2? So to determine this, of course, first minute, nothing to DQ because everything is empty. But in every minute, to do this step, you will, to determine which customer you will DQ, we are going to generate a random value. I'm going to show you later. Okay. But over here, okay, in the second step, remember just I told you every minute we have 2 steps. First step is we DQ the customer from the counter, right? Second step, we are going to enqueue new customer to the queue. And just now in the scenario description, we will encounter every minute there are 3 new customer, right? So here we have customer, we use the number to indicate different customer, like 0, 1, and 2. So we have customer 0, 1, and 2 put to the queue, and then we check which counter is empty. We will DQ the customer from the queue to each of the counter. So now customer 0 will be counter 0, customer 1, counter 1, and customer 2 in counter 2. Right. So this is the first minute. So in the second minute, okay, we will continue with step 1 again. Remember, step 1 and step 2 only every minute. So step 1 is we have to DQ the customer from the counter, right? Now, how do we determine? As I told you, for every counter, you need to generate a random value. Okay. So this random value, like in our scenario description just now, we say that every counter you use probability of 0.3 to determine whether it finished serving the current customer or not. So if the random number that you generated is a value less than or equal to 0.3, you are going to remove this customer from the counter. Means this customer finished already, then it will go. So the counter becomes empty. If the value that you generated is more than 0.3, you do nothing. Do nothing here means or this customer will remain there in the counter to continue with the transaction, for example. Okay, so based on the random value I generated in this 3 counter, only counter 1 or counter 0, okay, has a value less than 0.3, right? So this customer 0 is like, will leave the counter. We finished already. So now counter 0 will be empty. But counter 1 and counter 2, because the random number I generated is a value more than 0.3, so this customer 1 and 2 will remain there. They haven't finished. Okay, so this is the step 1 in the second minute. Then we go to step 2. Step 2, okay, again, we will enqueue the newly arrived customer. There are 3. Now the customer number is 345. So we enqueue inside. Okay, and after you enqueue to the queue, you're supposed to look at which counter is empty now or counter 0. So you will put customer 3 because according to the queue, customer 3 comes first, right? So you put customer 3 to counter 0. This is the end of the second minute, right? And then in the third minute, you do step 1 again. So determine which counter to DQ to remove the customer. So you generate random value again for each of the counter here. So based on our value, if it's at value less than or equal to 0.3, you are going to remove the customer from the counter, right? Means the customer will leave. So based on this value, counter 0 and counter 2, the customer will leave, right? Then this customer 1, because the value in counter 1 is 0.4, customer 1 still remain there, haven't finished yet, okay? So now, this is the first step. Then second step, you enqueue new, actually you should enqueue newly arrived customer first. 3 more customer, and then check which counter empty. So counter 0 empty, you put customer 4, counter 2 also empty, you put customer 5 there, right? And then there are 3 more customer inside. So you go to the start of the next minute, then you enqueue 3 more customer, okay? And then basically, these are the process of the simulation. You just have to remember in every minute, right? You only perform 2 steps. Step 1 is generate a random value for every counter to determine should you remove the customer from the counter. Okay, it's like they finish their transaction already, so they will leave. So the counter will become empty, right? If not, they will remain in the counter. Then in the second step, you will enqueue newly arrived customer to the queue. And you check after you enqueue which counter is empty, you put the customer there. Okay, then you repeat, you go to the next minute and repeat step 1 and 2 again. This is what you do in every minute. So how do we implement this in the program? Okay, so this is the program. You can see here, we are going to use queue, right? So what I need is, of course, I need the queue, right? To put the customer there. So the queue, the value that I store inside is int, integer only. So integer is to represent the customer number only, which customer is there based on the customer number. And then I also have counter, but the counter here, if according to our scenario for the simulation, we say we only have 3 counters, right? But here I can use an array to create my counter where the size is 10. It's like, you see in the bank, usually when they have many counter, but usually they don't open all, right? Let's say they have 5, maybe they open 3 only. So we can do something like that, where here I also create a lot of counter, I create 10. But I will use this value available counter to determine how many counter I'm going to open now. Okay, not all 10. Maybe now I open 3 first and I run the simulation to see what is the scenario at the end. Okay, or 3 cannot, maybe the queue very long at the end after the simulation. Then I increase the available counter, let's say to 5, and then I run again and I see what is the scenario at the end. Okay, we can do something like that. Okay, then I have this variable prop to represent the probability finished serving the customer. Just now the value is 0.3, right? And I have this customer number to indicate which customer you are serving now, starting from customer 1, 2, 3, 4, 5, and so on. So over here, before I start the simulation, I will actually set all the counter to 0 first, means no customer there. If the counter value is 0, no customer there. And I will use a for loop to simulate how many minutes I run. Here, let's say I want to run for 100 minutes. So I will look from 0 until 99 here, right? Then I perform my step 1. In every minute, you have step 1 and step 2. So in step 1, what I do? Generate random number for every counter, right? To determine should you remove the customer or not. So this is what I do. I will here I will use a loop. Then how many times I loop depends on how many counter I open. If here my available counter is 3, means I open 3 counters, right? So I will look 3 times. Each time I will generate a random value for each of the counter. So if my available counter is 3, so I generate 3 random value. Then I check if the random value I generated is less than or equal to 0.3, 0. Else you do nothing. You don't have to do anything if the probability is more than 0.3, right? So this is how we remove the customer from the counter. We just set it back to 0. Okay. So this is my step 1. How about my step 2? Right. So my step 2 here. So in my I need to enqueue newly arrived customer, right? Okay. In the scenario, it's mentioned that every minute I will have 3 customers arrive. So how do I enqueue this customer to the queue? Okay, here I also use a for loop. I also look 3 times because 3 customers, right? So every time I will remember the enqueue operation in the STL, the function is called push. Okay, so you put queue.push customer plus plus. Why I need the plus plus here? Because this is to indicate the customer number. So initially my starting customer is customer 1. The value is 1. Then the second time when I push, it will be customer 2 because you plus plus. Then customer 3 and 4, 5, 6, and so on. Okay. And after this, I will move. After I enqueue 3 customers to the queue, now you check which counter is empty. Okay, so for all the counter that I have, available counter, if this counter K is 0, means no customer, then I'm going inside here. I'm going to what I do. Okay, I'm going to actually pop a customer, the customer that is waiting in the queue and put in the counter. But here I have to check if my queue empty or not, because even though your counter empty, but no one is waiting, so we cannot move. There's nothing for you to, no customer for you to put to the counter, right? So that's why here we will check whether the queue is empty or not. So here, if it's not empty, means there is still some customer waiting in the queue. I will put the front customer, queue.front, in counter K, because counter K is 0. Okay, and then pop out means remove this from the queue. Okay, so this is how we move the customer to the counter, right? Okay, let me show you the output of this program. We still have time. One. This one, okay. I think I don't need to compile because I have the exe file here. Okay, let's see. Okay, so this is the first minute. You can see here, first minute simulation. In this program, right, that I show you the output. What I show you in the slide is just the program that do the simulation, but without any output. Okay, but this program that I run here, I add the function display simulation so that it will display what is in the counter, which customer in the counter, and then who is inside the queue and so on. So I add this function inside. Okay, and then inside the main here, I will call the function to display the counter and the queue. Okay, so when I run, this is what I have. So it will print out the content in every minute. So let's say for the first minute, first step, check if counter finished serving or not, right? So it will generate random value for counter 0, 1, and 2. Here I only have 3. Then when counter 0 finish, because for those that have probability less than or equal to 0.3, I will print it out. Like here, only counter 0. But because first minute, of course, your counter will be all empty. So there's nothing for you to see. Okay. Then in the second step, we enqueue newly arrived customer, right? So you can see in the queue now, customer 1, 2, 3 are waiting. Okay. Then only I move the customer to the queue to empty counter. Because from here we see that counter 0, 1, and 2 are all empty, right? So customer 1 is in counter 0, customer 2 in counter 1, and customer 3 in counter 2. Right. That is the end of my. This is my thing. So now my counter 0, 1, 2, I have customer 1, 2, 3 inside, right? So what I will do, I supposed to generate random value, right, for each counter to determine should I remove each of these customer. But based on my output here, it means all these 3 counter, the random value generated is more than 0.3. That's why these 3 customers still remain there. But then I go to the next step and queue 3 more customer, 4, 5, 6, and I check any counter empty. No, right? Because these 3 are still waiting there, are still doing the transaction. So I have 3 customers waiting in the queue now. Then I run my third minute simulation. So in the third minute, okay, when I generate the random value, counter 1, 2 actually has value less than 0.3. So just now the customer, that they leave already, but counter 0 still have customer 1. Then my queue from the previous minute, I have 4, 5, 6, right? So in my second step here, I enqueue 3 more customers, 7, 8, 9, and then check which counter empty. Counter 1, 2, so I put customer 4 and 5 inside. But in my queue now, I have these 4 customer waiting, 6, 7, 8, and 9. You see? If I run again the next minute, okay, we can see that in the next minute, when I generate the random value, only counter 2, this customer leave. if the other two counter, the customers still remain there, then my queue now have 4 customers, right? And when I enqueue 3 more customers to my queue, you see, now my queue has 7. Then I move any empty counter, yes, counter 2. So I move customer 6 to here, but my queue still have this 6 customer waiting, you see. Then I just continue to run my simulation, and you can see that here at the end, more customers are waiting in the queue. And then the next minute, more customer. The next minute, more customer. Okay, so it means that, okay, in this scenario, if I until 100 minutes, right, at the end, when you check the content of the queue, there might be still a lot of customers waiting there, you see. Okay, so if that is the case that you have when you run this simulation, it means what? It means that the scenario that, or the scenario that you are having, like for example, you open 3 counter, it might not be enough to serve all the customers. Okay. Another thing that you can change is maybe you can change to open more counter. Let's say instead of 3, you can set the value to 5 or 6. Then maybe your queue will become shorter at the end, right? Another thing that you can change is the probability. You see, the probability here that we use is 0.3. So when I generate value for the counter, like for example, if it's less than or equal to 0.3, then only I will remove, right? But if it's more than 0.3, I won't remove. The customer remain there, which means your counter is not empty and you cannot put the customer waiting in the queue to the counter. They are still waiting, you see? Okay, so you see, your probability 0.3 is actually very small. Let's say when you generate probability, right, the possible value you get is 0 to 1. So to get a value within 0 to 0.3 will be smaller than to get a value that is starting from, let's say, more than 0.3 to 1, right? 0.3 to 1, you have more probability to get it, you see? So if you change your probability, let's say to 0.5 here, means if the value you generate is a value less than or equal to 0.5, you remove the customer, right? So the chances for you to remove the customer from a counter will be greater than 0.3. This is something like maybe your worker work faster. Okay, this probability. Okay, something like you ask the worker, okay, please do the operation faster. So you change this probability, then you will see the content of your queue also will be decreased if you do that. Okay, so you can basically when you run this simulation, right, you can play around with all this value to see, okay, if your scenario is like this, with this probability, with this number of counter, then what you get at the end. Okay, will this satisfy your requirement? Okay, let's say, is it enough to serve all your customer? So if you find that if your queue is very long at the end, then it might not be sufficient what you have. Maybe you need to open more counter. So you just try to run the simulation again with different scenario. Okay, so this is just an example for a scenario where we have 3 counter, 1 queue. We can also, you can try to, for example, case here, you have, let's say 3 counter, and every counter has its own queue. You can change from the program here. I mean, if you want to simulate that one, you can do something like, means that now your queue, you have each queue for each counter. So your queue, you can change it to an array where every one is for each of the counter, like Q0 is for counter 0, Q1 is for counter 1, and so on. Then you change accordingly in the code here. Of scenario that you have. Okay. Okay, so let me just conclude. Okay, so this is our last example, how to use Q to do simulation. Okay. So, okay, these are some of the references that you can refer to. Of course, when you go to the internet, there are much more than this. Okay. Another thing is, if you are interested in Java, or let's say you are actually using Java, Java also they have library for data structures, or you can also implement from scratch. So you can look at this link here, number 4, is for data structures using Java. If your language is Java, okay, if you are not using C++, okay, because I don't have time to cover so many languages, okay, here. So I think that's all for me. So now, is it Q&A or? Yes, okay, you ask why don't we open all the counter, right? That's why I say this is just a scenario that we set. Okay, because at the beginning I told you the scenario is we open 3 counter first. Even though I have 10, right? I just want to open 3 first to check. Okay, I run the simulation with 3 counter, and I want to see at the end how long is my queue. So if my queue is very long, it means that, oh, maybe I open 3 is not enough. Then when I can run the simulation again. Now I open 5 counter, then I run again and I check. So at the end, or maybe is okay, it's better than just now, but maybe there are still some customer waiting there. So maybe you can open more, maybe open 6 or 7 or 8. So you can try to change this value. Okay, you can open all if you want. Yeah, this is the corner, pro and con of using more counter. Okay. Why don't they just open all without checking? Okay, as I told you, because you see, let's say in a bank, why don't they open all the counter at all the times? Because sometimes I mean, non-peak hours, you might not have that many customers, so you don't need that many. And you need more staff if you open more. You see, maybe you don't have that many staff. You see? Okay. So this is for you. It actually based on the requirement that you want to simulate, because you want to find out under this scenario, right? Is it adequate if I just have 3 counters and then my probability is what and so on. Okay. For the test is CPP and Java. Yes. You can use both. Yes. Okay, any other question?
None from my side.
Okay. The PPT and the example, I think we will give to the organizer to be shared with you all. I'm not sure when will the video be uploaded. This one I think you need to ask the organizer. Okay. Any other question? If no, then I think that's the end of this workshop. Okay. So I will end the workshop now and pass the mic back to the organizer.